Hello, chemistry students. I think in another video I might have said I was going to not do significant figures this year, but then I changed my mind, so here we go. So we're going to roll through this, and hopefully it doesn't turn into astrophysics made simple there. So briefly I'm going to go over just kind of the scientific method-y stuff that we see on a pretty much yearly basis, but we do try to follow through this when we complete experiments and you know, have hypotheses and then test them with experiments and find a conclusion. Alright, so let's just talk about the difference between quantitative and qualitative really quickly. So quantitative data is going to be numerical in nature, while qualitative data is descriptive data. So things that you can't put, or at least when you report it, you don't put a number to it. So color, shape, texture, smell, descriptive. Think about adjectives there, and I guess some nouns might fall in there too, but descriptive terms. Alright, measurements are quantitative, and we will take lots of them, or at least deal with lots of them in calculations as well. So there's a number, and then there's a unit or a scale to tell you some kind of meaning to go with that number, because without a scale or without a unit, numbers kind of become sort of meaningless when you're trying to describe the physical world. And even if you say two, it makes a lot more sense if you say two people or two oranges, so you know what you're talking about. All right, so yeah, here's some examples. And I think it would be worth me mentioning that when you report your answers, unless you happen to be answering in a ratio, all of your answers in chemistry should have some kind of units. That's a way to not lose points. All right, so let's take a look at... Alright, so I'll put you some page numbers in there. So here's SI units for different quantities that we may measure, and particularly we'll be working in the grams, or usually we'll use grams instead of kilograms in here because of the amounts of things that we measure, and maybe some kelvins and some moles are going to be the ones we use the most. Anyways, you can take those units and put them together and make derived units, like meters squared would measure area, or meters cubed would measure volume, and then you can put volume together with mass and get density, which I'm not sure I actually see on the chart here, but it's a thing, grams over centimeters cubed, for example. Alright, so with that said, there's always going to be a certain amount of uncertainty in measurement, and that'll usually be the last recorded digit in a number. Now sometimes we have to put placeholders to make the number the right size. Like, for example, if you estimate that there are 180 marbles, but you're really not sure it's actually 180, then the 8 would be an estimate, and the 0 is just a placeholder to hold to make this number the right size, because if you just wrote down 18, that wouldn't quite be right. Okay, why is there uncertainty? Well, you're performing measurements with instruments, and you're not going to get like an infinite number of decimal places from any instrument that you like a scale or a ruler or something like that. And some measuring devices are better than others, like this electronic balance is going to yield more certainty in measurement than this spring-based scale. Alright, so let's talk about the difference between accuracy and precision. So accuracy is agreement with a true value. whereas precision just refers to getting agreement within the multiple measurements that you make in the same way or fashion. And you might think, well, that's crazy. Why would you measure something multiple times and get something different? Well, if you've ever used a tape measure to measure, for maybe a carpentry project or just generally building something, you might have noticed that if you measure things carefully, a lot of times you do actually get within a very small tolerance, but slightly different measurements each time you measure something. Or two people might look at the measuring tape and see something slightly different. So there is a certain amount of uncertainty that goes with your measurements. Now, this first illustration here shows that you're not getting the right answer, you're not hitting the target, and the arrows aren't particularly close together, whereas the second illustration shows that you're still not hitting the target, but the arrows are much closer together. So this will be a precise but not accurate. This is like you forgot to zero the scale before you started weighing things, and you're always a few grams too low when you are making your measurements. And sometimes that might be okay, and sometimes it would absolutely not be okay. All right, and then if you're consistently getting the right answer and your measurements are always close to each other, then that is precise and accurate, which is where we would like to be. All right, so there's different types of error. Random error is the kind that's probably okay, and that's equal probability of being high or low as long as you keep it to as small an amount as possible. Whereas systematic error means that you are doing something consistently wrong that causes the error to be off one direction or another. Now, this is really the meat of this, and that is how we count significant figures. So the significant figures are going to be things that we actually measured in our experiment. And because of the way our number system works, it's necessary for us to have zeros, and zeros are the only digits that sometimes are not significant, and the only reason why they're not significant is if they serve as placeholders in a number, but sometimes zeros are significant. So the first rule here about which digits are significant or indicate measured quantities is easy. Everything that's not a zero is always significant. So 3, 4, 5, 6, that's 4 significant figures. All right, so the rules for zeros, leading zeros, those are zeros in front of a number. Those do not count as zeros. So this 0 here and the 0 here come before the number actually starts. They're to the left of the first digit in the non-zero numerical part of this number. And by the way, if you have 0.00000, if there's nothing there but zeros, that's not a measurement. All right, so anyways, that has 1, 2, 3 significant figures. All right, captive zeros, if those are between non-zeros, those are easy because you measured them because they were in between these non-zero digits. So 16.07, that 0 is significant. All the non-zero digits plus the 0. 1, 2, 3, 4 significant figures. All right, so trailing zeros are not as easy because they're significant only if the number contains an expressed decimal point somewhere. So here's an example, 9.300. Well, those zeros are trailing and there's an expressed decimal point in the number. So if you got a 0 after a non-zero and there's a decimal point expressed, then those are significant. So 4 significant figures there. All right. Exact numbers are not limited to any particular number of significant figures. For example, if you have a conversion, I'm actually not a big fan of this one. We're going to assume that all of our conversions are like this, but this one actually isn't. A better example would be that there are 12 inches in 1 foot, or there are 100 centimeters in 1 meter. Those are defined quantities and they're exact. Another way is you can get at that is there is 1 orange, or there are 2 people. Things that can't be subdivided are also have infinite significant figures. There's no lack of precision there. All right, so let's go through and identify the number of significant figures in each of these. Perhaps pause, get your finger on the pause button and pause it. All right, so this one, 5 significant figures. These 2 zeros are significant because they're captive. This is 0 because it's trailing, and there's a decimal point expressed. Okay, this one, the answer is 4. That 0 is significant because it is trailing and there's a decimal point expressed. All right, this one is 5 because these 2 zeros are captive, so they are significant. This 0 is trailing and there is not a decimal point expressed in the number, so that 0 is not significant. Oh, what to do with this? All right, this is 3 significant figures. This is just a power of 10 out here. That would be similar to putting placeholder zeros in. So scientific notation, look at the number in front of the scientific notation to determine how many significant figures it has. Disregard anything about the 10 there. All right, this one. All right, 2 significant figures. Why? Because the leading zeros here, those are never significant. If you wanted them to be significant, there would have to be another number out here in front of that 0. All right, this one. That's only 2 significant figures because, let's think about, oh yeah, these are trailing zeros and there's not a decimal point expressed. If you put a decimal point right there at the end of the number, that would be indicating that you had measured all of those zeros. All right, so I think I'm going to actually break now and do the second part in another video. So tune back in to the next video.